Welcome to second part of the video. We are going to show a practical demo by designing AXI-Lite adder with the Corsair tool, and we will generate the hardware and firmware and documentation for the site. So I'm going to generate a new project. We are going to define registers for the Corsair tool using a text file. So let me create the text file. In this text file, we are going to define the adder definitions in a markdown table. So I showed in the example. So here we have three registers, two input registers and one output registers. All registers are 32-bit wide. First register is at 0th address, which is A register, and second register is at address 4, which is B register. The last register is at defined at address 8, which is sum register. Here we specify A and B as an input to the system. So that means from the CSR module, these two are outputs which are going to connect to the core logic. Similarly, the result is input to the CSR module. That's why we defined I as a hardware. Since the result is not writable, so it's only read only. But other two registers can be read write. So this is the input corner for the register definitions. Let us go for CSR config file. The CSR config earlier we defined the following things. So let us copy paste those things from this file. I'm going to create a new file, CSR pic, and we'll paste those things. Now our register map is defined in the adder.reads.text, and we're going to generate a Verilog module in this file, hardware/adder underscore registers.3, and similarly we're going to generate software components, and we'll see markdown document in the docs folder. Now we have both register definition file and CSR config file. Let us go and run the Corsair. Before running, let us see, because we have only these two files in this folder. The Corsair tool will read both files and generate the hardware, software, and components. So here we can see three folders were defined: documentation, hardware folder, and the software. So now let us go and see what is inside documentation. So this is the markdown format for the documentation, and we can preview this markdown. So this is the register map. This is the register map documentation for the our given register conditions. We have three registers which are as per our definitions. A register at the 0th location and B register at the 4th location and some register at the 8th location. Since we use 32-bit, we don't have any bitwise definitions here. Then we can go and see hardware. So adder_registers.b was defined with the following interfaces. There is an AXI-Lite interface, and there is a clock and reset, and there are input and output ports defined to be connect to the core logic. We mentioned A, B are output to the CSR. So these are the output values from the CSR module which are going to connect to the core logic. In our case, it is adder, and this is the sum, and this is the sum port which is input to the CSR module. Let us create the top level adder module, the AXI-Lite interface. I'm going to define a new file. This AXI-Lite adder. I can keep this thing aside. Okay. So we have adder_edge at the left side, and we opened a new file AXI-Lite_adder.p on the right side. So let us go and define AXI-Adder with the same parameters as defined for AXI-Lite interface. Copy paste them. And we'll have clock. You can see like we defined the reset as a negate. That's why this was done like this thing. So we will have an AXI-Lite interface at the top of the module. So we have added our top level clock resets and the AXI-Lite interface to this thing, which is shown as in our diagram. Showed it is the diagram. So we defined the AXI-Lite and other clock and resets here. Now we are going to instantiate AXI slave logic, which is our adder_registers module, and we are going to add a core logic. Either we can add the core logic as a separate module, or within the top level module we can add. So we are going to add core logic, which is our adder logic at the top level itself. So let us define the internal signals. Logic 31 down to 0 for our A register, and similarly B register and the sum register. So now we can have a port logic Now we can define the code logic here. I'm going to assign sum is equal to MSP. Now we will use the AXI module instantiation. In our case, this module is this one. So I'm going to add a image instance. So I'm going to just define the input output ports along with the AXI-Lite interface functions. So with this we conclude our module. Let us go and test this module with the OpenTV test bits. So for that I'm going to define a makefile first, and similarly Python test builds file, which is test_axi_added.file. So I'm going to define the variables and other things for the makefile. So let me open the makefile. Python file and the file. So I'm going to define top level language as a Verilog and sim as stars, and just equal the with all times are with respect to the makefile. So we should give all our source files and test files with respect to the makefile. So we are going to add Verilog sources. Verilog sources, which are like we are going to add AXI-Lite adder, which is our top module. And similarly, Verilog file for our listed definitions. Which is in hardware folder. Adder. So these are the two source files we have, and our top level module is AXI_adder, and our module name is our Python file name. Is the module test stands for AXI_adder. So we are going to include the simulation files, simulation make files here. So okay, now we finished our make file. Let us fill the Python test page. So we are going to import OpenTV, and we required a plug from CocoDB.clock, we are importing clock. Similarly, from triggers, we are importing rising rates and clock cycles, and then next time step. So before going to write a full test bench, let us write a simple hello world test so that all compilation of the files is going to define CocoDB test is async takes the BTS check. I'm going to generate clock. Period 10 nanoseconds. So we'll wait for we'll start the clock. And wait for 10 and wait for 10 seconds. So this is a simple hello world test bench. Like I'm generating 10 clock cycles and starting the test. You can see the waveform also to observe this clock generation. So let me go back. So I'm going to run make file. So which says our hello world test is passed. That is, all our files are compiled and they are good. We can set waves variable, set environment variable to 1 and run it again. You can get a waveform. See in the sim build folder, you can see there is a fast signal trace file AXI-Lite underscore adder.txt, so which can be opened using GPK. AXI-Lite adder is our top module. Since our test bench is Python, so DUT itself is the top level. So let us go and trace the clock. You can see there are 10 cycles and there is no further waveform because we started the test after that. So now let us go to the test bench and add our other components. But apart from generation of clock, we require to we are going to generate a reset for this thing. So I'm defining a separate reset value. In the DUT, we had a reset name as RST, but the polarity of this reset is negative. So I'm going to define this reset like this thing, and you can remove this hello world test and add the actual adder test. Simple adder test I'm going to add here. So we are going to generate a plot. And we are going to generate a reset also, and we can wait for reset to come out. Since our DUT has AXI-Lite, so we have to import the AXI-Lite from the PocoTB extension AXI. So we are going to import AXI-Lite bus and AXI-Lite master. This AXI-Lite master is the one which is going to interact with our DUT on the AXI-Lite interface. Okay. So here I am going to get the AXI-Lite master. Our DUT has AXI-Lite interface with the prefix AXI, and our clock is CLK and the reset is RST, and our polarity is reset is false, which is active low reset. Okay, so we defined AXI-Lite master and we started reset, and we are waiting for the DUT to come out of reset. So here we can use AXI-Lite master to write to the 0th register, which is our A register, and I can write to the B register, which is defined as a 4 address. Okay, and we can read back the result, the weight, and we are reading from the 8th register, which is our sum. So we can insert this result with our expected value, which is 1 plus 2, which is 3. Okay. So in case if this is not going to work, like we see a failure, so we can say, we can put a formatted string. When it failed, we can show what is the actual result. So now I can go and run the test again. There is a syntax error, I think. So since our bit is by capital bit, we have to read B word. So AXI-Lite master defines the right B word, which reads 32 bit. Similarly, this one also. So we can check the waveform of the AXI-Lite transactions as well. So this our simple adder test is passed. we can add more tests. Here we added the, so here I can add a random generator test. So let's see. But instead of typing directed values, we are going to write some randomly generated values. Okay, so before going to that, we can check the waveforms from our previous test. Let me record the waveform. Let us see the waveforms of the previous test. Here we write A and B registers and write the sound register. So let me add A address, A right. Let me add AXI-Lite AW channel. Similarly, write data channel. We'll add clock and we'll save. We'll see the transactions. We'll see the AXI-Lite transactions. Here, address 0, we have written data 1, and address 4, we have written data 2. And there is a ready and valid handshake on AW channel, and similarly there is a ready valid handshake on write data channel. So let us add AR channel, which is address read address channel. So we are reading address 8 here, and there is a ready valid handshake data channel, which give result 3 as a R data. Okay, now we can add the random test cases for this thing. So where I am generating, say, for I is equal to range of 100 values I am going to generate. Here I generate A as random integer. Which is between 0 and 32. 2 power 32 minus 1. Similarly, B also, and we have to import the random. So now we'll program our A and B registers for this thing. We read back the sum registers and put into the result variable, and this should be the value should be A plus B. So this should be A plus B, and out of that we have to take only 32 bits. To say this is the expected value. So in this case we are ignoring the carry and other things. So let us open the test. So this random test generates 10 random inputs of A and B. And you can see in the log there are a lot of AXI-Lite transactions. And the test, both simple adder and a random adder test are passed. So we can see the waveform for this thing. If you refresh the waveform, you will see a lot more transactions on the AXI-Lite. So these are like 100 transactions which we define the random test case. So far we have defined our AXI-Lite based adder to design using, we defined the AXI-Lite register module using the Corsair tool, and we used that AXI-Lite module in our AXI-Lite adder top module, and we defined the core logic, and we have tested this module using CocoTP.